Hey everybody, here we are going to try to do one more example, graphing a rational function where m is equal to n. I thought I was going to be able to do it because I put him down and I felt like I could write faster, but I was about to hit record and he came over and did the little thing like pick me up, you know? All right, expanded form is how I'm starting. If this is the first video you're watching, I suggest you go back and watch the first one I uploaded, which was 2x squared plus 3x minus 20 over x squared minus 3x minus 10. So I'll call that like chapter 18 part 1. This will be chapter 18 part 2. So go find that. I explained everything more in there, and then I did, I don't know how I'm going to break this up, because this is m equals n part 1, and then I'll have m less than n part 1. I don't know what I'm doing yet. We're figuring this out in real time. Okay, sorry, carrying on. That's expanded form. Everything on top is expanded, standard form, descending exponential order, but I also want to look at factored form. I would factor an x out of the top, so f of x equals, if I pull out the GCF of x, I'm left with x squared minus 36. That's the difference of two squares. So I would get x plus 6 and x minus 6, the conjugates. On bottom, I will have a GCF of x again. So if I pull out x, I am left with x squared plus 8x plus 16. That factors to x plus 4, x plus 4. So I end up with x plus 4 squared, because I have two of them. Now, this is factored form. This is also going to be our first example where we have what we call a removable discontinuity, because we can remove x over x, that reduces to 1. It's still a discontinuity. It's still a restriction. X still cannot equal 0, but it's not an infinite discontinuity. It's not stuck there forever. What's an infinite? Infinite discontinuity. So the infinite discontinuity is the vertical asymptote. They are stuck in this equation infinitely. They can't be removed, like a removable discontinuity, and the branches will approach the infinities when we have one. As for the removable discontinuity, a nickname for those is a hole, and I will show you what that looks like as we go. Okay, again, this is a crash course, not super in-depth, but doing the best we can. And the instructions are, nope, wrong thing. Here, these are all the instructions. And you should also see, we are going to elaborate on this whole information about a hole. So anything, if you need to screenshot that, don't get my face. You could screenshot it, do what you got to do, save it. But this is my content. Don't steal it and act like it's yours, because, you know, my hard work. Okay, so let's get moving. I'm going to talk out everything that's written here, but it's there. So x-intercepts, everything we do after we remove our removable discontinuities, we don't leave them there. We have to get rid of them because they're going to cause a lot of problems. So I need x-intercepts come from factored form. Okay, x-intercepts. So I have two of them. Where are they? They are at -6 and 6. That's where they are. I'm going to label them, and they're both to the first power, so that means they're going to behave like linear. So -6. They've been shooting a movie outside my apartment, and they have like old cars, like model cars, like, I don't know, 70s maybe. They smell really bad, but it actually smells like something's on fire right now. Like, it's really concerning. I don't know if I should stop recording and get up and go check. I mean, there's people out there. They should be able to smell it too, like if there was a fire. I'm not being so responsible, right? Oh man, it smells really bad. Like the cars, they smelled really bad. And like, I forgot how much like modern technology and modern rules have made cars smell less bad, and electric cars especially. Oof. They towed them here, and they just only started them to move them for the scenes, and smelly, not good. But oh, something smells like something's burning. Oh, it's really bad. I'm sorry, I'm so distracted. Y-intercept we get from our constant term over our constant term. I can't see one there in the original, right? But that's because of that hole when x is 0. Could I figure out what it would be here? So it's a little sneaky. I could. What would be my constant term over my constant term? On top, I would get negative 36. On bottom, 4 squared I would get, because I'm filling in 0 for x essentially, that's 16. Negative 36 over 16, it's negative. It's negative 16 times 2 is 32. So it's negative 2 point something if you want to reduce it and be, you know, nice and fancy. Oh, x-intercepts I should have written as negative 6, 0, and 6, 0. So the y-intercept would be 0, comma, divide by 4, 9 over 4, negative 9 over 4. So that is 0, comma, negative 2.25. There. It smells really bad out there. Oh my god. Hopefully it's not any of my grow lights on my plant. I don't think they would. I feel like still a little concerned about it. Okay, there's my y-intercept. Next, vertical asymptotes I get from my denominator, setting my denominator. I know we're saying we set it equal to 0 to solve, but you're really setting it kind of like not equal to 0, like, hey, it cannot equal 0. So what value would cause my denominator equal to 0, since that's not allowed, and that's why we draw an asymptote? X plus 4 equal to 0, so that means x equals negative 4. So that's my vertical asymptote. So here, negative 4, and the power on that is even. And, ooh, a little aggressive, my bad. The delta tango rule that I brought to the YouTubes tells you what? It tells you that the multiplicity of the factor will tell you if your branches are both pointing in the same direction or if they're pointing in opposite directions. Even multiplicity tells you that the branches are both pointing up or down, and we'll figure that out based on everything else. And last but not least, we are doing our end behavior. So if I look at this, now it doesn't matter if I do this before or after I removed the hole, the removable discontinuity. Either way we look at it. For my horizontal asymptote, I am looking at leading terms having the same power. So it's either x cubed, so LT over LT. It's either x cubed over x cubed before the hole, or it's x squared over x squared after I remove it. So either way, it's 1 over 1. So y equals 1 is my end behavior. Okay? So that is y equals 1. So my graph will approach 1 as I go out to the sides. Now, what about this whole blabbing about? What is the crazy lady talking about? Okay, here. If the numerator and denominator contain common factors, they are removable. The matching factors can be divided out to 1. Anything over itself is 1. Only if it's attached by multiplication and division, stopping that person that cancels, reduces or simplifies things from the top and the bottom that are attached with addition and subtraction. No one is impressed by that. That is so wrong. Stop doing it over and over and over again. You're embarrassing yourself because that's not allowed. I'm just going to be honest with you, and if no one else is going to tell you, I'm going to tell you. It's embarrassing when you cross out, like in the original problem, the x cubed over x cubed. If you did that, that's embarrassing. Stop doing that. I'm just telling you because no one else will. The matching factors can be divided out to 1. However, the existence of such a factor in the denominator still creates a discontinuity. Unlike an infinite discontinuity, which presents as a vertical asymptote in the graph, pink, a removable discontinuity presents as a hole in the graph. To find the coordinate point of the hole, so really it's just like one removed point. It's just like a teeny tiny hole. That's it, but we'll make it really exaggerated with a big circle. These are not holes. These are big fat x-intercepts. A hole is like an open point, not colored in, not used, but we're exaggerating with a big open circle, okay? To find the coordinate point of the hole, again, I'm going to talk you through it in a second, but the words are here. Set the removable factor equal to 0, solve for the x coordinate, okay? Then remove the removable factor, okay? Evaluate the remaining rational expression at the x coordinate. The result is the y coordinate of the hole. Okay, ready? Let's go. So take the removable factor, x, set it equal to 0 to solve for the x coordinate. So, okay, x equals 0. Great. I need the y coordinate because it's going to be an ordered pair. Take that x value and fill it into the remaining rational expression. So 0 plus 6 is 6. 0 minus 6 is negative 6. 6 times negative 6 is negative 36. 0 plus 4, 4 squared, 16. So coincidentally, I mean, think about it. The hole is at 0 comma negative 2.25 or negative 9 over 4, right? It's at my y-intercept. My y-intercept is a hole because the original problem is telling me that x is not allowed to equal 0. So I know I colored it in green, but I'm going to go with my white out right now. And I'm going to kind of white that out because it's really not allowed. I'm going to draw an arrow. I'm going to write the ordered pair, 0 comma negative 2.25. And I'm going to label hole. It's just a hole. You treat it like a point, like you pass through it like any other ordered pair. However, it's basically indicating, hey, this one little glitch spot, there's no graph. It is what it is. So I could still treat it like a point. I could connect through, right? So that's linear. I'm going to pass through. Got to approach my asymptote. There we go. Here, I can't ever bounce off the y-axis. Got to go like this and approach that asymptote down. Even asymptote power, so that side must also be down because both sides have to be doing the same thing. I have an x-intercept. I'll pass through pretty straight, best I can, but I got to turn and ride along that asymptote right under it. And there you have it. Is that the best drawing I ever did? Probably not. Is it horrible? A little. Sorry. What about the domain? Negative infinity until negative 4. Negative 4, I run into an issue. Union, negative 4. After negative 4, I'm good until the hole, 0. After the hole, bloop, jump over it, 0. I'm good until until forever. Domain, done. Range from bottom to top. Now, while this y value is excluded, I don't need to exclude it from my range because it is included here. So, you know, it's accounted for. And it looks like I'm riding up against this asymptote until forever and into the sunset. So from negative infinity, the range always starts at the bottom, until positive 1 with a parenthesis. Because I'm using all the y values between the bottom of the graph all the way up until right up against that asymptote. So there you have it. Another example. I'm doing elaborate ones so you can see all the worst case scenarios. Most of the time you're going to see examples that are a little simpler than this, but I just want you to kind of cover a lot of ground in one example. Okay? All right. Thumbs up for sleeping puppies. And thumbs up for that smell going away. And hopefully nothing burned outside. Questions, comments, concerns, requests. I take requests like a DJ. Put it in the comments. Check the description box for the playlist, or just go to the actual playlist. It's in a thumbnail at the end. And I don't know what I'm saying anymore. Bye.